Please read the important announcements before we get to the business at hand. My task this morning is to introduce the Michel Boudart Award. Michel Boudart was my mentor, my colleague, and my friend. This is not working. Michel was born in Brussels, Belgium, in an accident of history, as many of our own ancestors and ourselves. He crossed the Atlantic and reached our soils to study with Sir Hugh Taylor at Princeton. He then taught at Princeton for a few years. He then taught at Berkeley, and then at Stanford. 30 years ago, I was a student of Michel Boudart at Stanford, and I have been a student of Michel Boudart ever since. His impact, next slide please. His impact in catalysis is of course in my own subjective view unmatched. In our concepts of the active sites, in developing structural reactivity relations, and in teaching us about how to measure reactivity as the basis and part of catalytic processes. Next slide, please. Well before the dynamism of catalytic sites was, I think, well recognized and publicized, it was Michel Boudart that introduced us to the fact that we should not look at one time and in one place, but we should look over time as the reaction is taking place. And this is a direct quote that he wrote in his usual elegant and very lucid use of the English language.
That was the identical sizes, as well as one could judge at that time, of those support clusters, and the dependence of the catalytic activity on the support. And Boudart accepted the language of the time that the supports were acting as ligands. So we're going to hear that thought repeatedly this morning. Then there's a third paper by Boudart. This one's 1997 that I want to mention, because I especially like, and I think I did at the time if my memory's good, the words near the top that are in red or orange. Let's read those words. To promote heterogeneous catalysis to the rank of molecular catalysis. And this is Boudart writing this. And so some of us would like to think it is taking the rank of heterogeneous catalysis upward to make it molecular catalysis. This was not a widely accepted viewpoint at the time he wrote that. But I do think it was motivating a number of us who were working in this field at the time. And some of you are here. And I don't know whether you remember this paper, but I do. Other words that showed up here were build a surface. So the implication is it's about synthesis. And so Boudart was realizing what was going on in this part of the community, and that there was catalyst preparation going on in ways that were not conventional and could be described fairly as synthesis. We're not using metal salts, putting them in conventional ways on supports and making supported metal catalysts in an economical way. Rather, we're trying to make them in ways to make them structurally simple and understandable. So be driven by the science rather than the technology in that sense. And you see the words at the bottom that I've highlighted, the idea of making molecular catalysts as a collection of identical single sites of uniform activity and selectivity. Well, that's my goal. That's what we're talking about here. So in that very same paper, and notice that there was a kind of provocative title to that paper, whether this was reality or an oxymoron to talk about molecular catalysts on surfaces. Boudart went out a bit on a limb, and he looked at several examples and came to the conclusion that it was a fair description to call these molecular catalysts on supports.
So I just want to mention a couple of the examples he chose because they're important work, and lots of you will know this work. So part of it goes to the work by Van Haag and colleagues, in which they were investigating ZSM5 samples, a whole family of samples with a wide range of aluminum to silicon ratios, and therefore a wide range of densities of proton donor sites, if you want, catalytic sites, on the surface. And he used those catalysts for cracking of normal hexane and found a measure of catalytic activity, not the one we would most want today, to be linearly dependent on the aluminum percentage of aluminum sites among the T sites in the zeolite.
And so a number of people, we included, were referring to that catalyst as a kind of ideal one with well-defined catalytic sites. The other example that Boudart chose was related to his own work, and it tied to work from Ertel and Koch, who were using palladium single crystals for CO oxidation, and the Boudart group was using that same test reaction, but with supported palladium particles as the catalyst. So Boudart went so far as to suggest that we might classify these catalysts as being essentially molecular and having essentially identical catalytic sites. But
these reactions have drawn people's attention in the intervening years, and we realize today that we wouldn't use those terms to describe these catalysts. They're more subtle than one had first wanted to think of them as. And it's not just a proton donor site, it's a proton donor site in its surroundings that makes it a catalyst. And within the zeolite, almost any zeolite, there's a variety of those surroundings and a variety of catalytic sites. And the same with surfaces of metal.
So this really implicitly poses the question, how can we get catalysts that are coming closer to this ideal? And it leads to the notion of synthesis.
So this is central to this story. We're going to be talking about how to synthesize a number of catalysts that are intended to be in the category of structurally uniform, with all the catalytic sites being the same. This is still a challenge, but I think there's been progress in the intervening years, and that's really the same with, see those iridium atoms migrate, see them form dimeric species, trimeric species, and ultimately blow up the zeolite as the clusters become too big to fit in the pores. So that's first kind of evidence of the structural uniformity of the sample. Here's another one. We're back to the cyclohexene hydrogenation reaction. I'm going to quote some results from Rick Finke's group, the very careful kinetics experiments often done by that group. And so they took the zeolite YHY, zeolite supported iridium complex, use it with liquid phase reactants to do this hydrogenation. Follow what's going on spectroscopically, and I'm showing XF spectra in this case. So what happens as the temperature goes up, hydrogenation of the ethylene ligands takes place, we make some ethane, we make some other hydrocarbon ligands on the iridium, we start breaking iridium-oxygen bonds to start unlinking the cluster from the support, and then most important in the blue curve that starts at the bottom at the left, shows that we're making metal-metal bonds. And over the course of this experiment, the number of near neighbor iridiums, determined by XF spectroscopy, goes from 0 to very nearly 3, within experimental error 3, corresponding to a 4-atom tetrahedral cluster frame iridium-4. And so this process is an in situ synthesis of the cluster on the support. It's clean chemistry. It's not clean with rhodium, for example. You make a mix of clusters with rhodium, but it turns out to be clean. You get a very stable cluster frame in the iridium and the iridium-4. So here are the Zanes data showing that transformation, the cluster formation, isosbestic points showing the stoichiometric simplicity of this. The process is reversible. We can oxidatively fragment the cluster by treating it in ethylene. And we can go through cycles of cluster formation, cluster breakup, and so forth. So some rather clean organometallic chemistry on the support surface and characterized by those isosbestic points. There's another way to make supported clusters, and it's a ship-in-a-bottle synthesis. This has been done many times for many years. I'm just going to illustrate briefly making iridium-6 carbonyl from the mononuclear iridium precursor in sodium Y-zeolite. And these images are probably not showing up very well, especially for those of you in the back. So I've highlighted the iridium atoms with blue and with red to show the little 6-atom clusters hiding in the pockets of the zeolite pores. And here you can see them, at least in the lower middle, you can see the iridium atoms after we've decarbonylated this, and I put a little helper there showing the location of the atoms in case you can't see that very well. So the important point is we've encapsulated the clusters in cages, and we've retained the nuclear 6 after we've decarbonylated. So there's a whole family of catalysts like this. I won't go into detail about these. We've done it both with rhodium and iridium and done lots of characterization and lots of catalysis. And the long and the short of that is these are complex, and to understand what's going on in the catalysis has not been so easy. So this work is not new anymore. It was represented in a kind of cartoonish way. And you can see all the data we had are consistent with this interpretation. Pi bond the olefin hydride, hydrogenation, make the alkane from the alkene as a reactant. So there's a whole family of catalysts like this, and this was related to the early work that Boudart was commenting on. Today we can do better. We can start understanding catalysis by iridium-4 clusters. And this emerges from very careful synthesis work. This is the work of Alex Katz, who's used these big, bulky calixarine phosphine ligands to bond to the tetrairidium cluster, and he can support this on silica. So let's look at a schematic of this. The tetrairidium cluster has phosphine ligands, big, bulky ligands that are affecting the chemistry a lot, bonded to the basal plane. So the blue iridiums have these big bulky ligands, but the apical iridium does not. And what the Katz group learned how to do is to tweeze out the CO from the apical sites, selectively oxidize that CO to make CO2, and open the site selectively at the apical iridium. And what the catalyst characterization and catalytic activity measurements show is that the rate of reaction is directly proportional to the number of opened apical iridium sites, and that linear dependence that you see on that curve shows that each of those iridium sites is equivalent. So this is another single site catalyst. And the support's a different kind of support now. It's not a metal oxide or a zeolite. The support's a fragment of the cluster. The support is a 3-atom fragment of the tetrairidium cluster. And so this extends the class of supported catalysts that are atomically dispersed. Let's now go from metal clusters to metal oxide clusters. Lots of people have done lots of very nice work with catalysts like polyoxometalates, sometimes on supports. These are not the easiest to work with. Characterizing them does leave some open questions. Let's look at a different metal oxide cluster and realize that we can disperse it in a way that leads us towards the goal of making all the catalytic sites uniform and using these as supports. So here's a simplified version of this metal oxide cluster, 6 zirconium atoms, 8 oxygen atoms. This is metal oxide, so it's going to have surface chemistry, such as hydroxyl groups or aqua groups on the surface. So we're now going to look at this dispersed within a crystalline material, a MOF, a metal organic framework. So what's a MOF? You get a MOF by combining a node, which could be as simple as a metal atom or a cluster like the one I'm showing, combined with an organic linker. Under favorable conditions, the self-assemble and make a crystalline structure that exposes the sites of the nodes within the open porous structure. So this is a large class of materials, tens of thousands of MOFs now. I will fearlessly predict there will be a new one discovered today. And remember that zeolites, we have about 200 to work with. In MOFs, we've got tens of thousands. So there's a lot of open space for novel catalysis and novel catalyst synthesis within the zone of the MOFs. So the MOFs we're going to talk about have linker precursors that you see here, so they can react to become dicarboxylates, for example, on the left. Those can react with the node surface to oxygens bonded to two zirconiums, for example, to link it all together into a crystalline porous structure. So just be very brief, we're looking at a couple of MOFs that originated from our colleagues at the University of Oslo, UIO66 and UIO67. You get an idea of the porous structure from this representation. You see the nodes, you see the linkers, and you get the idea that they're pores, and some of these have quite nice large pores that make them rather easily accessible. Others have smaller pores that make you think about mass transfer limitations. Okay, so let's just talk a bit about the synthesis, because that's an important part of the story here. So the synthesis of one of these MOFs involves use of a precursor, metal salt, zirconium chloride, for example, the linker precursor, and then other components, including water, and including components that we call modulators. And all these are competing, these modulators and linkers are competing with each other for sites on the metal oxide cluster that forms at an early stage of the synthesis from the zirconium salt. So there's subtlety to the synthesis and a lot of empiricism. So just want to emphasize here with this cartoonish representation, we've got water present, the modifier modulator is present, the metal salt's present, and under favorable conditions these self-assemble. People characterize MOFs by X-ray diffraction crystallography and BET surface area measurements, but we're going to need more than that. Okay, so here's schematically, if we start on the left with the metal oxide cluster, you see linkers bonded to some of the sites, not all of them. Some of those sites are going to be open, call them defect sites if you want, some of them will be defect sites. And so one can get various groups bonded to the surface of the nodes. So you see some of those on the right. So this is cartoonish because we don't fully understand this, don't fully control this chemistry yet. We're not the only ones working on this. Part of what one can do is to start dialing in specific sites on the node surfaces. So for example, take what's initially present, postulated to be sites that have hydroxo and aqua groups, treat with methanol, make alkoxide, treat with water, make hydroxo, and now we've got something that looks like a metal oxide surface and looks like a support for our catalyst. So let's go back to the very same kinds of precursors we've been talking about. Here's iridium diethylene ACAC compound. It reacts with that node surface, anchors the metal complex, and gives us now a MOF node supported metal complex catalyst. And here's an image. You can distinguish the nodes that have iridium from the nodes that don't because of the intensity differences here. You see structure of the MOF, and thanks especially to Nigel Browning and his colleague at PNNL for doing this microscopy, which is very challenging because these are very delicate materials. But the other thing you can notice if you just look at this is there's a subtlety to this chemistry. There's dynamics going on in the material that distinguish the MOF from the zeolites. Lots to learn about this. All right, so we made the supported iridium catalyst, and now let's put it on the plot that we saw before, showing catalytic activity for ethylene hydrogenation versus that measure of electron donor character from the infrared spectra of the metal carbonyl on the support. And what you see here is that the MOFs, and I've listed the two I talked about, and there's another one, NU1000, The MOFs fit right in with the pattern that has emerged from the data with the zeolites and the metal oxides as supports. So they're all a family, and an important characteristic of the supports as ligands is their electron donor character. But if we look at the infrared spectrum of the iridium gem dicarbonyl, compare that for the MOF with that for the zeolite, we get a kind of stunning result. Those bands are sharp for the zeolite, we saw that already, but for the MOF, they're broad. The sites on the MOF node surface are not all equivalent. We have work to do to understand how to master the chemistry, the surface chemistry of the nodes within those MOFs. So if we're to strive for the uniformity of catalysts that I think we've demonstrated with zeolites, we have to be stronger in controlling and dialing in the chemistry of the node surfaces. And it's subtle because there are missing sites, missing linkers, there are defect sites, and there can even be components remaining from the synthesis that are bonded to the surfaces of the nodes. All right, let's get close to the end here. I'm watching the clock if you're getting nervous. Let's talk some more about a support that is structurally non-uniform, the heterogeneous surface of MgO. We like MgO because even in powder form, it's crystalline, and we can get excellent images of various crystal faces in the powder material. It's a poor person's surface science, MgO science, okay? So now we're going to use a heavier metal that I haven't talked about before, osmium, so we can get good contrast in the microscopy. We start with the triosmium. You see it in the upper left. You see the triangles. You see 3 osmium atoms together. This is an interesting history with this one because we were making samples like this a few years ago involving collaboration with one Johannes Schwank, one Larry Allard, a microscopist, and a graduate student named Boudart, who remembers, smiling because he remembers this work. All right, so you can break up these clusters of oxidative fragmentation. The oxidizing agent is just the hydroxyl group on the surface. We get isolated single atom species. And we have these in the form of a metal carbonyl. Now we look at the image, and what's interesting about this image is we're looking, so we've got the 110 face, we're looking down on columns of Mg and columns of O, and see where's the osmium, and we find it's on top of the columns of Mg. And the only way to rationalize that observation, comparing it with XAF spectra that show us metal oxygen distances, of course the osmium is bonded to the oxygens. The only way to reconcile the observations is to realize that the osmium is present at a defect site. It's present where a magnesium is missing, and otherwise it doesn't make any chemical sense. So this raises the question about the defect sites on typical catalyst supports. Are most of the supported single atom catalysts that people have been working with on oxide supports characterized by metals at defect sites? Well, I'm starting to ask a rhetorical question, and we'll finish with the question. So some of you heard a talk by Louise de Bev earlier at this meeting. She showed a number of images of iridium on MgO, and various MgO samples treated in a number of different ways and with a number of different loadings of iridium. So if you see the high loading of iridium at the left, you see lots of isolated iridium sites on the MgO. But if you go to a very low loading, and we're not the only ones working with these low loadings, 0.01 weight% iridium in this sample, look, you see the iridium atoms. Are they all the same? Are they all in the same kinds of sites? To be continued. So let's summarize. What we're talking about here is molecular chemistry on support surfaces. We see evidence from a number of techniques of isolated single atom complexes and metal clusters. We can start doing chemistry with these, much in the way that organometallic chemists do solution chemistry with their soluble catalysts. catalysts. And so we've got bases for rational design emerging for this class of catalyst. We see we've got a lot of levers to pull in how to make the catalyst and control what it is and what its surroundings are, including what its ligands are. So there's a field that's now burgeoning and seeing lots of contributions at this meeting and rapidly growing literature to this broad field. Back to what we talked about at the beginning, there are important industrial catalysts in this class, so we believe there's lots to happen yet that can be valuable in this respect. It's time for me to say thank you, first to the Hydrogenation organization for sponsoring the Michel Boudart Award. This supports our field in a powerful way. Thank you for all of us. Thank you to the NACS, to the FCATs for supporting this award. And thanks to a lot of people who've done most of the work that I've talked about here. So you see names of a few grad students and postdocs near the top. And a big group of collaborators from various places who've helped us enormously and made this research very enjoyable. And thanks to the funding agencies that have supported this over time. Thank you very much for being here and listening.